Okay, in this video we're talking a little bit about ice charts. So ice charts are a tool we can use to solve for the equilibrium position of an equilibrium problem. Okay, the ICE in ICE chart stands for initial, change, and equilibrium. Okay, so just a brief guideline of rules that will often work. They won't always work, but usually they'll help you think about how to solve an ice chart problem. So first thing we need is a balanced chemical reaction. Dr. Kenny, my immediate predecessor at CASE, used to call these Rice charts because the first step is to have a balanced chemical reaction. The balance part is really important because when we start determining the change values, we're going to use the stoichiometry of the reaction. Next, we can write an equilibrium expression using the law of max action. Again, the equilibrium constant is going to depend on the stoichiometry of the chemical reaction given. We can list our initial concentrations. The ICE chart is going to contain concentrations. If you're working with Kc, if you're working with a Kp, it could use pressures. So for the example we're going to do today, we'll be using concentrations. So we put the initial concentrations into the ICE chart. You can calculate Q to determine which direction the equilibrium is going to shift. By knowing if Q is greater than or less than K, we can determine which way the reaction is going to go. This isn't always necessary. In today's example, you'll see that the Q value is going to be 0. It's going to be less than the actual value. But if you ever have something that's 0 in a chemical reaction, you know the reaction has to be shifting towards that direction because that's just how it works, right? We can't go the opposite direction because we don't have any of those components to react to shift, okay? But in this example, we'll calculate Q anyways just to see how it's done. Then you can define the change needed to reach the equilibrium. Again, this depends on the stoichiometry of the chemical reaction. And then we can define the equilibrium concentrations by using where we started and the change that occurred. We can substitute those equilibrium concentrations into the equilibrium constant K and then solve for the unknown. Often you'll have to use the quadratic formula, but sometimes it's helpful to try to solve problems without using the quadratic if you can. Then you can check your final results by plugging your equilibrium concentrations back into the equilibrium expression to see if the K value matches. Okay. So this is a set of rules that will sometimes help us solve some problems. So if we take a look at this problem, we have a 3-liter flask that contains 3 moles of hydrogen gas, 6 moles of fluorine gas, and we're given an equilibrium constant at a given temperature, and we want to know what the equilibrium position is. Okay, so it says calculate the equilibrium concentration of each component after the reaction is complete, so you have to think about how much both reactants and products is present. Okay, the product of the reaction is HF. And because we're given an equilibrium constant, this applies to only a particular reaction. So in this case, the reaction is just with stoichiometric coefficients of 1 in front of the hydrogen and the fluorine. Okay, so we can go ahead and get started. First thing we need to do is write a chemical reaction. So we can write H2 gas plus F2 gas is going to reach equilibria with 2HF. Okay, so we know that's our chemical reaction. We can then write a expression for K from this chemical reaction. So K is going to be equal to the concentration of the products, in this case HF, squared, raised to their stoichiometric coefficients, divided by the concentration of the reactants, in this case hydrogen and fluorine. Okay, and this has a value of which is equal to 115. Okay, remember the equilibrium constant is unitless, and so we just have to remember when we're solving the problem to plug our values back in. Okay, we can calculate a Q value for this reaction to determine which way it's going to go. So Q has exactly the same expression as K, except they're non-equilibrium values. So in this case, we've got our initial concentration of HF squared divided by our initial concentration of H2 divided by our initial concentration of F2. Okay, So we need to solve for each of these values. So we can do that just by looking at the problem. So our initial concentration of H2 is going to be equal to 3.00 moles of H2 in 3 liters. And so that gives us a concentration of 1 molar H2. We do the same thing for fluorine, and we get 2 molar. And because the problem doesn't mention anything about our HF concentration, we should assume that we're starting with 0 molar HF. Okay, so then we can plug these values all into our equilibrium expression. We've got 0 squared divided by 2 times 1, which is equal to 0. Okay, so Q is less than K, so the reaction shifts towards products. Okay, so we can see that this is immediately true because we're starting with 0 HF. So since the reaction is going to occur with atoms colliding together to drive the reaction either towards reactants or products, if we have no HF molecules to collide, the reaction cannot go towards the reactants. Okay, so now we know our initial concentrations. We can work on our ice chart. Okay, so the initial conditions we just calculated. So for hydrogen, it's going to be 1 molar. So the values go into the ice chart in terms of molarities. For fluorine, it's 2 molar. And for HF, it's 0. Okay, so then the change is how the reaction is going to change as time goes on. So for our H2, the stoichiometric coefficient is 1. So we're just going to define a variable that's the change. So in this case, minus x. It's a minus because we're removing reactants to produce products, so the concentration of reactants is going to decrease. Fluorine also has a stoichiometric coefficient of 1, so minus x. And then our fluorine, our HF is going to increase. So it's going to be plus 2x. And so the 2 comes from the fact that we have a stoichiometric coefficient of 2 in front of the HF. So at equilibria, the E part of our ice chart, we're going to have 1 minus x. For fluorine, we're going to have 2 minus x. And for HF, we're going to have 2x. Now we can plug these values into our expression for K. So K, which is equal to 115, is equal to 2x squared divided by 1 minus x times 2 minus x. Okay. And so at this point, we're just solving a algebra problem. Okay. So we're going to need to refer back to this. I'm going to delete this ice chart. But so if we remember, this is where we're going to eventually go. So we'll come back to there when we get back to the slide in 1 second. Okay. So now to do the math, we'll use a quadratic. If you have some sort of tool to help you solve a quadratic in an easier way, be sure to use that. Oftentimes at this point in the problem you want to think about, are there any ways you can simplify the math? So if there's a square on both the top and the bottom of a fraction, it's often much easier just to take the square root of the entire thing and work from there. So 115 is equal to 2x squared over 1 minus x times 2 minus x. Okay, so this is just from the other slide. So now we can square this top part, and because the 2x is inside the parentheses, we'll have 4x squared divided by, and then we can FOIL out the bottom, and we'll end up with 2 minus 3x plus x squared. Then we multiply this bottom times our 115, and so we'll end up with 230 minus 345x plus 115x squared is equal to 4x squared. Then we can subtract the 4x squared from both sides, and we'll end up with 0 is equal to 111x squared minus 345x plus 230. Okay, then we can solve this as a quadratic where this 111 is A, negative 345 is B, and 230 is C. And then the quadratic formula tells us x is equal to the opposite of b plus or minus the square root of b squared minus 4ac divided by 2a. So what we can do is we can plug the values in, and so we'll have, so this is equal to positive 345 plus or minus 345 squared minus 4 times 111 times 230 divided by 2 times 111. And when you solve this, you get x is equal to 2.14 molar or 0.968 molar. So the quadratic formula will always give two answers. There can only be one correct answer, so one of them has to be wrong for some reason. Sometimes you'll find a negative concentration. You can never have negative concentrations. In this case, they're both positive, so we can't necessarily eliminate one just by the sign. But if we were to go back to our ice chart, we saw that the concentration, the equilibrium concentration was 1 molar minus the change. So if our change was 2.14 molar, we would get a negative equilibrium concentration, which doesn't make sense. So therefore, 2.4 has to be incorrect. So the correct change value is 0.968 molar. Okay, this is not the answer to the question, right? The question didn't ask about how much it changed. The question asked about the equilibrium concentrations. So we can find those by looking back to our ice chart, and we see that the concentration of hydrogen is now 1 molar minus 0.968, this change value, so it's 0.32 times 10 to the minus second molar. Our fluorine concentration is 2 minus 9.68, so 1.032 molar, and our HF concentration at equilibria is going to be 1.936 molar. We can check this to make sure our answer makes sense by calculating K, by plugging these values in. So we have 1.936 molar divided by squared, right? That value is going to be squared, divided by 3.2 times 10 to the minus 2 molar divided by 1.032 molar, and that's going to end up giving us about 114. Okay, and that's very close to the 115 that's given the problem. Everything seems to be making sense. So this is the correct equilibrium position. These are the correct values for the equilibrium concentrations. Okay, so that hopefully shows you how to do some ice chart problems. There's an activity you can do that will help you solve some more problems. It starts off with a very simple example that you should be able to solve without a problem after you've seen this video. And from there you can do some more complicated ones, and it gets into some really nice ideas like the 5% rule. So go ahead and work on that, and good luck.